Please welcome Lindley, who's going to talk about algebraic effects and effect calculus.
Okay. I don't know why you're applauding before I start. Yeah, okay. So in fact, Daniel Hillestrom was originally supposed to give this course, but his employer wouldn't let him take a holiday. So I already had material on this, so I said, oh, I'll try and present that again. And the slides I have, actually, I originally gave at OPLSS a couple of years ago. And there I had 90-minute sessions rather than 60-minute sessions. So I don't know exactly how this will go, but I'm not going to worry. I'm going to we'll go through it and see where we get to. So I'm going to give a very high-level introduction to algebraic effects and effect handlers. And you've had a whole lot of category theory over this morning and yesterday. I am not going to use any category theory at all, although there is a nice categorical story about this, and a lot of this work was originally studied in that setting. So, but I'm going to try and be quite concrete. So let's start off with a little quiz. What is an effect? Can we have some answers to that question? Jamie, what? Oh, I better not ask you. Ask Philippa then. What do you think an effect is? Interesting definition. I mean, Jamie, why don't you go ahead and say what you think an effect is? Any other ideas about what effects are? The useful thing that comes out of a program, right? Now, that's an interesting one. A change of state. Okay. I think most of these are reasonable answers. What's a pure computation then? Without effects. Philippa. Fair enough. Oh, and then what's an effectful computation? Well, I guess a computation that has effects, I guess. Yeah. Okay. Anyway, yeah, I just wanted you to sort of think about what you think effects are, and I'm going to give you my account. So, in the nice sort of clean accounts of semantics that we often start off with, we might idealize programs as just black boxes, take inputs to outputs. That's it. But when we actually come to write programs in the real world, they have to actually interact with their environment and do other things. In fact, typically they don't go directly to the outside world. They might go through some sort of runtime system or operating system. And yeah, I would say that an effect is anything, any kind of interaction that isn't about just this black box computation. I guess I don't actually explicitly have this on my slides. Well, okay, it'll sort of come up. There is a sort of subtle distinction between well, I mean, I guess the question is, what is your environment? You might actually be interacting with the outside world, but we also talk about effects internally inside a program, where you want to think about your program interacting with another part of the program. But we'll come to that. And yeah, there's all kinds of different things that we class as effects: I/O, concurrency, distribution, exceptions. We might even talk about certain kinds of choice as effects. And in conventional programming languages, these things might be just built in language like C or Java or JavaScript. And their semantics is maybe not particularly well specified. It's just there. And there's a very practical problem with this sort of hard wiring as well, which is each time you have one of these effects, it might not be quite the thing you want. So, for instance, or at least the choices about how it behaves are built into the system. It's quite hard to customize. So in JavaScript, for instance, there are several different notions of concurrency, and all of these models get implemented separately, and it's a bit of a mess just to maintain the thing. So this is sort of the motivation for what effect handlers are all about, and they come from the theory of algebraic effects, which then motivated effect handlers. And they're supposed to subsume all of these things. That's the idea. And in fact, this whole line of work started off with work on monads, which I think, well, they're connected to adjunctions, as you saw in Chris's lectures, but in the context of denotational semantics, they were introduced as a way of modeling effects. And then that led on to work on algebraic effects, which led on to effect handlers. And at the moment, I'm being very hand-wavy, and I haven't said anything about what these things are. I will get to that. So important properties we have of effects and handlers is that they're actually composable. We can define different effects and plug them together, and they can be defined inside your programming language. So they are related to some other things that people may or may not be familiar with. I'll come back to that in later lectures, actually. Relationship between monadic reflection and effect handlers, and also delimited control. And they're also not just a theoretical thing. They're having quite a bit of impact in practice right now. OCaml 5 now builds in effect handlers, which are used for building all kinds of concurrency abstractions. For several years, GitHub was, every time you did a pull request, I think, it would run a library that fundamentally depended on effect handlers. The React library that is used for many websites does not have effect handlers in it, but the design of it is very much inspired by that. A thing I'm working on, I should mention Pyro as well. That's a language for doing probabilistic or stochastic reasoning used by Uber, and that does build in effect handlers. And I've been working on adding effect handlers to WebAssembly as well. Again, as a very low-level construct, a target for a whole range of different features. Now I'm going to give you another zoom in slightly, and still at the high level. We had this picture of your program talking to the outside world. We can view effect handlers as being kind of like composable user-defined operating systems. So if we expand out that box there, this is kind of your pure program. We can actually, don't know whether this, yeah. You can define lots of little operating system-like things, and these are handlers in a kind of stack. And your program is programming is written against some interface. These shapes represent my interface, and then different handlers like this one might handle the circle and as a triangle and so forth. And then some of them are pure; they don't access the operating system at all. Some of them might access the operating system and go to the outside world. So that's kind of where we're aiming at. But now I'm going to go back to the details. So yes, we have this view of pure computations as black boxes. How might we model effectful computations? So I'm just defining a BNF in pictures here. We have these interactions. We might also I mean, the most basic thing a computation can do is just return a pure value. But if you have some kind of interaction with the outside world, we call this an operation. The interaction then needs to be, I mean, actually, I say outside world, it's going to be an interaction with another bit of the program, the handler. It's going to return one of k values, and then you just continue. So this gives you a sort of rather abstract model of effectful interactions. So here's a concrete example. So supposing we have operations for reading and writing Boolean state. I can get a Boolean, or I can put a true value into my Boolean state cell, or put a false value in. Then I might have you can view this as like a sort of denotation of a computation here, which is just going to, what does it do? It reads the state. If it's true, then it's toggling it. Yeah, it's putting false into the state, and then we're going to return the true value, but the state's been updated false, and then it reads false, it puts true in, and it still returns the false state. So very simple program. We can also describe, or at least conceptually, we can describe interactions where you have a domain that is not finite. This is an infinitely wide tree that is just implementing increment on a state cell. Does this make sense so far? Good. And this is an example I'll keep coming back to, non-determinism. Here we have two operations. We have choose, which returns a Boolean, and we have fail, which returns something in the uninhabited type, which means, well, it can't return at all. It fails, it's an exception. And what's the idea here? Oh, we're going to make two choices. The first choice is to decide whether, I mean, I guess maybe I should demonstrate. I'm the drunk coin tosser. So I might, if I'm drunk, I might actually drop the coin and I get no result at all, and then I end up over here. And then the second choice is, well, I catch it, and then I had to get heads or tails. I got tails, I think. Yeah. Okay, so a couple of simple examples. So this is my starting point for what an effectful computation is. It's just one of these command response trees. Yeah, we can write it a bit more concisely like this. So either you return a value or you perform an operation, and these are the continuations of your computation. They're the rest of the tree. Turns out that it's actually convenient to write it in this kind of continuation parsing style as well. If you have lambdas in your function, you can take in a result, take in this x, and based on that value, you pick one of these computations. And then that would allow you to, for instance, write that increment function, which was infinitely wide. Right. So just, again, showing you some the examples we had before. This is the tree we had, and that might correspond to a program in a real language that would be written more like this. You read the state, and then you put the inverted, you toggle the bit. Or you might, the increment function looks like that. And the drunk toss function looks like that. So one way of looking at this is, well, these are direct style programs, and these are denotations of those programs. Although so far, none of these things actually have any meaning. We're just building these trees up. So in a sense, this is still just a form of syntax. Okay. So if you are familiar with monads in Haskell, for instance, then it's worth knowing that, in fact, these command response trees are just instances of the pre-monad construction, where, yeah, you just build up these trees, and the bind operation basically just performs substitution. It takes if you have a return and bind, you just substitute it in. Otherwise, it propagates through all of these continuations. In fact, this rule is an interesting one, because that actually defines the property that characterizes what it means for a theory to be algebraic. It says that, basically saying that bind commutes with the continuations of operations. But now I'm going to now I'll tell you what algebraic effects are. So an algebraic effect is, well, it's like what we've seen so far. You have a signature of operations, but in addition to that, we have a collection of equations. So if you take the Boolean state example, we had these operations, and we have kind of the obvious equations you might expect. If I put twice, then I can discard the first one. If I do a put followed by a get, then I don't need to do the get, because I know that I'm going to get back the value I just put in. If I do a get followed by a put, where I put back in the value I just read out, then I don't need to do anything. If I do two gets, similarly, I can just do that as one get. Just as an aside, turns out that last equation is redundant. You can show. I don't think I need to go through that, but it's a fun exercise to prove that. But yeah, the point is that this is essentially all that algebraic effects are. You have these trees, and then you quotient them by equations, and that defines the behavior of a particular effect. So how about, I mean, this is in contrast to the way in which at least monadic effects in, say, Haskell are taught. It says nothing about how you'd implement these things. And that's what I'm going to talk about now. I'm going to give a denotation of the state example. So I'm going to just, an obvious way to implement these computations is as a function that takes in the input state, and as well as returning the interpretation of the value, it returns the updated state. And yeah, this essentially it amounts to your standard monadic interpretation of state. So if we just have a value, then the state remains unchanged and we return the interpretation of the value. If we do a get, well then, if we're in the true branch, then we get M. If we're in the false branch, we get N, and we thread the state through. If we do a put, then we update the state. But we can give other interpretations to this. We might say, well, I don't care about the final state. So this is basically the same except for the return case, where we don't return the final state. Or we might want to do something else. We might want to return a list of all of the states that we've ever seen. So in the return case, you just get the initial state. The get case doesn't change, but the put case is going to add the new state onto the list. Yep.
Now, what would satisfy the equation of compulsion?
What equations? Oh, well, yeah, exactly. Right. So the point here, well, which I'm going to get to anyway, is I might write programs in terms of these get and put things, and I might want to do all of these things at different times with that program. You're absolutely right that what equations get satisfied changes depending on what implementation you use, but they all seem like reasonable things I might want to do. I might be debugging my program, so I want to log some extra stuff. But yes, indeed, if we look at the standard one, then it is unsurprisingly sound and complete with respect to the equations. And if we ran that toggle example, oh right, yeah, this is just the interpretation of the toggle example. Then it does what you expect. You get the pair of things out. If we take the one where we throw away the final state, well, this is sound with respect to the equations, but it isn't complete because, because I might, if I do a put followed by a return, well, I throw away the final state, so there's those two are not distinguished. So yeah, that toggle example actually is equivalent to the identity function because we don't care about the final state. And as you said, the logging interpretation isn't sound with respect to all of those equations because, yeah, if you do, if you change the number of puts, then well, you get a different answer. So yeah, this is motivating. This is not the original way in which effect handlers were motivated, but it's motivating the way in which they are nowadays used. The point being that it's useful to write a program to an interface and have various different interpretations of that. You might, for instance, want to write a non-deterministic or probabilistic program, and you might want to get distributions out. You might want to sample from those distributions. You might want to do all kinds of different things. And yeah, that amounts to basically, I've shown you these equations, and what people now do in practice here is throw them all away, which is a bit of a shame because they are useful, but that's and there are more refined things you could do. Like you could say, well, okay, in the logging example, the equations do still hold, modulo recording a whole load of information that is only about logging. So you might want some way of distinguishing that and saying, yeah. Yeah, anyway, so basically going forward, we're basically going to be throwing away the equations. And I'm going to refer to my computations as abstract computations.
Sorry. Why we put in because not every interpretation is
So, I mean, okay, there's two different answers to this. I've motivated it because it's inconvenient, because actually we want different interpretations. We want to be more permissive. It's useful to have interpretations that violate some of the equations you might think hold. It would be nice to be able to tame that. A different answer, which is the pragmatic reason why effect handlers in practice don't use equations, is the same reason that you don't enforce the monad equations in Haskell. It's that it's a pain if you have to prove all these things every time you write a program. Maybe if you're doing this in a richer language like Idris or Agda or something, then you might do that. But and there are lots of examples that are really useful of these things where we don't even have equational presentations, and they're not even known.
So is the idea that you want to take the control away from the equation into some kind of programming artifact?
Yes, we get some. I'll show you eventually. We get to useful examples. This is sort of the historical way in which effect handlers were discovered, but their usage is actually quite different. Okay, so now I'm going to actually move on to what effect handlers are. If we go back to this interpretation, a different way of writing this same thing is to recall that there's basically one continuation for every possible value that get could return. So you could actually turn that into an actual function representing the continuation. This is just the same thing. It's just that this k here is a function that's going to take a Boolean. You actually get a more concise definition, but it's the same. And then having done that step, we could say, well, let's turn that into a language feature. So you can define this inside your programming language. There is a slight difference here in that this one is defined recursively. We're recursively invoking the meta-level interpretation. Here, this R, which stands for resumption, implicitly wraps the same handler around it. So it's also recursive, but this is a... Sorry? They're the same. They're exactly the same thing. It's just I've reified the construct in the programming language, whereas before I was just talking about meta-level interpretations of the thing. Yeah. Yeah. Oh, that's just a unit. That's the unit value. Because there's only one return. Put only has one continuation. Yeah, we're just witnessing the standard isomorphism between products and functions. A product is a function from indexes to things, which isn't so important there, but imagine you had an infinite number of these, then we couldn't write it down. But whereas we can write a lambda down that operates on natural numbers.
What's the meta? What does that mean? In contrast, what interpretation can be?
I'm reifying this construct in my object language. Whereas before I was just sort of saying, well, I write some syntax over this thing and then I define a semantics. I mean, it's like the difference between having a language where you say oh, I have some effects built in, and I can give a semantics for that whole language, versus the language we're ending up with is I don't have built-in effects. If I want to define one, I can actually write them in the language itself, which is what this. Oh, well, I'll show how that goes in a minute. But I'm going to just show you another example along the same lines first, which is non-determinism. So we interpret non-determinism as a non-deterministic computation returns a list of things. So if you do a choice, you concatenate the two lists of the continuations. If you have it fail, which is the unit of non-determinism, you return an empty list, and return returns a singleton list. And again, you can replace that with, you can turn the enumerated continuations into functions, and then, yeah, as a handler, it looks like this. There's a small detail. It's convenient not to actually pull out rather than saying we have an infinite number of operations. Say if we'd have to have an infinite number of operations for put, you just say that your put operation is parameterized by something, but that's just a minor syntactic thing. So here's some example signatures we might have for state and non-determinism. Okay. What was I saying here? Oh, another thing, right. So with the non-determinism effect, we're returning this empty thing in the empty type. It's a bit more convenient to add parameterized operations. So rather than saying raising an exception returns something in the empty type, which means that when I eliminate it, I have to sort of explicitly eliminate it with absurd, which then will give me something of any type. We can give it this is a slight extension to the effects. We can give it this type, which says I can, if I fail, I supply fail with unit, and I can get back any type at all, which behaves the same as, yeah. What that means, it's just syntax. It's just saying I have an operation, so choose, which takes takes a unit argument and returns a Boolean.
What's the difference between that and
you can't run it's a completely different thing, actually. This is just the syntax for our signatures of operations. It is true that we have a way. Yeah, no, and okay. I'm kind of cheating here. There's this thing is not a function call. This thing, it says perform the operation choose, but for convenience, I'm writing it as if it is a function call. So you should think of them as being two different function spaces. And this one is kind of completely abstract and only means anything in the context of a handler. We'll see. It'd probably be helpful to show you some more examples. How far? Oh, yeah. So, take this example with choice and failure, and our drunken tosser example. Here's a function that for describing just a normal toss. This is the drunk toss, and then we might iterate the tosses a certain number of times, and drunk tosses is going to return. Yeah.
That's a type variable.
Yes. Yeah, you can think of it that way. Yeah, I mean, writing that there means that when I use fail, I can treat it as if it's polymorphic, which is exactly what you expect of an exception. If I can raise an exception anywhere, at any type at all, because I know it's never going to return. So yeah, now I'm going to actually show you some example handlers and how they compose. So most basic form of handler is an exception handler. So I should say this is just like a normal exception handler, except we have an additional clause that says what you do if you return a plain value. So this handler is going to handle exceptions by turning them into a maybe data type. So if you get a value back, you just return just X. If you fail, you return nothing. So if I handle 42, I get just 42. If I handle fail, I get nothing. And this is the syntax I'm using for handling. Now this is the respect in which handlers extend, or effect handlers extend exception handlers. You have this additional piece of information. This is the resumption I showed you before. And I'm going to give you a particular interpretation of choose, which is a rather boring one, that is just going to invoke the resumption with true. So it's always going to return true. So if I do one toss, then I just get heads. A more interesting one, and this is where some of the extra power of effect handlers comes in, is you can actually, this R, so this R is a function, and we can run it as many times as we like. So here we're going to run the continuation or the resumption once with true and once with false, and then concatenate the results together. So if you do one toss, you get heads and tails, because there was the one choice there. If we do something more interesting, we do drunk tosses of 2, the drunk tries to toss the coin twice, then we can stack the handlers together. First handling maybe fail, and then handling all choices. I should explain what happens if a handler, it's just like exception handling. If you try to handle an operation, so actually, yeah, if you try to do a choice, if drunk tosses try to do a choice and maybe fail doesn't handle choice, then it just bubbles up to the next handler. And if you do this, then it turns out you get this. And this list enumerates all the possibilities. The first one, let's see, I think that represents the case where the drunk tosses, the first line is when he tosses the coin, catches it, and it's heads. And then the second one might be heads, it might be tails, or they might drop the second one, in which case we don't get a list of 2 things back. And then this is the tails case, and again they might drop the second coin, and this is where they drop the first coin. So this is just illustrating that these things compose relatively nicely. I didn't give the other example I was expecting there, where you can compose them in the other order, and you don't get. If you do it in the other order, you just get nothing. But there's always a choice when composing effects together. You get to decide how they interact with one another. Okay. So now I'm going to show you what the operational semantics of effect handlers looks like. I'm omitting, I mean, you might extend a lambda calculus or some other language of this. I'm only talking about the bits, the parts that pertain to handlers. I'm not sure why I included let. Oh, no, I see, yeah. I have included let bindings here. Anyway, this first case is if you just have a value, so this is the return case, then you invoke the return clause. So it's just like let, really, and in fact, handlers generalize let. If you have a handler that has no operation clauses, then it is just the same thing as a let. This is the interesting one, and this is where all the power comes from. If I am in some evaluation context and I come across some operation, then I look up which operation calls it. I mean, I pattern match against this, and I substitute in the value for the p bit. Well, that's fine. But I also have to construct this r. And well, what is the r? The r essentially reifies the evaluation context as a function. Moreover, it rewraps the handler around the body of that function, making sure that in the continuation you handle operations in the same way going forward. Okay. I can show you some typing rules. So another thing that turns out to be quite useful if you're actually really programming in Ango with effect handlers is having an effect type system which keeps track of which operations a particular computation can perform. So I've given you some rules here, and so the idea is that you have effect types which are basically a collection of, it's basically one of these, a signature of operations. And then the type of a computation is a value with an effect type. If you want to perform an operation, then it needs to be in the effects that you're allowed to perform. We have a type of handlers. What does a handler do? It interprets one computation or one computation tree using another one. And it kind of does, well, the only thing it possibly could do. All of the operations here need to be in the effect that you're interpreting, and then all of the continuations, both the body of the return clause and the bodies of all the other clauses, they must have this other type. Crucially, the thing that you actually get back there from the R is something of type D, not something of type C, and that captures this idea that the body of the handler is also doing the handling in the same way. So I'm going to now give you various different perspectives in what these things actually are. So one view is that effect handlers are modular interpreters for effectual computations. I mentioned that there's this generalization of exceptions we had, but it's based on this extension to exception handling where you have a success case, and you can see that in the evolution of the syntaxes here. So normally with exception handling you might have try M with H, but Benton and Kennedy had this extension where you say try M, and if I succeed I'll bind the value to X and run N, otherwise I do H, and that's pretty much isomorphic to the syntax of effect handlers with except the return clause is written here rather than there. But and the other important aspect is that they're resumable. We get given this resumption. If you perform an effect, you don't have to just stop. You can do something else. There are also morphisms between free algebras. They can be seen as folds over these trees. Again, that's the business of you wrap the handler around the body of the thing, of the continuation, which means that it must handle the whole thing uniformly. And then also, if you know about delimited continuations, these handlers are just a structured form of delimited continuations, which is maybe not surprising with all this talk of continuations and resumptions. Yeah.
the function is trying not to ask. We both in a situation where we want to have more than one thing on the stack that I'm saying. So, when you say, well, it's like contact. A bit like problems. There's something we got around with these equivalent, not from X and Y.
Yes, there's an equivalent. Yeah, there's a thing named handlers corresponds to multi-prompt. So essentially, here the way in which you determine where the handler is you just dynamically traverse the stack until you find a handler that handles the thing. But if you give names to your handlers dynamically, then you can say, oh, I want to perform this operation and have it handled by this handler that has this name, and that corresponds exactly to. So I want to not got that much time, but I want to at least get to this example. Did I even? Yeah, I don't think I've actually shown you what a parameterized handler is, but you'll see it from this example. So what I like about the example I'm about to show you is it's actually useful and the kind of thing people actually care about, and what effect handlers, I would say, although they're very much give you a general account of effects, the real sort of killer app at the moment for them is concurrency. So what we're going to define here is an implementation of lightweight threads using handlers. So we're going to have just one operation, yield, and it doesn't take a payload and it doesn't return anything, it's just unit to unit. But yield just indicates that I'm happy to yield control to another thread. So really simple example, 2 threads, and we want to be able to interleave these appropriately. I'm printing things out so that we get to see how the interleaving occurs. I am slightly extending my notion of handler here so that the handler can take a parameter. And what that means is when I invoke the resumption, I get to update the parameter as well as providing the next value, the return value of the operation, which is just going to be unit in this case. And this is more or less the implementation of concurrency. We can actually make it even simpler when I move to shallow handlers, but I'll show you that later. But maybe let's look at this case. If our parameter is just going to be a collection of resumptions representing the threads we're implementing. Let's see. Yeah, so if the current thread finishes, well, what do? We just take the resumption at the head of that queue and pass in the rest of the queue as an argument along with unit. If we yield, then this R prime is the continuation or the resumption of my current thread. And again, we want to run the next thread, and we just stick the continuation of my thread on the end of that queue. And that's pretty much it. And then this is the case where the queue is empty, which is just going to keep on running this thread until it finishes. Yeah, slightly annoyingly, this is why a slight variant on handlers will make this easier. We really want to define this cooperate operation that takes a collection of threads, not a collection of resumptions. So a thread being just a func. And because if you look at these resumptions, they're all expecting this list of resumptions as well. There's a kind of recursive type going on. So this is just a bit of plumbing that this turns a thread into a resumption, handling it with this handler. And then if we get given a collection of threads, well, we need to turn them all into resumptions, and then, well, we run it with the identity thread, and it will go through more. Yeah? That is, yeah, so that's, it's, if we were currently running TA, we get to here, and exactly, it's everything after this semicolon here. It will just be print A2. What, the semicolon?
Yeah, I guess that's it. Like,
I mean, I'm just viewing that as syntactic sugar for let, where we throw away the value bound by the let. Yeah, I mean,
I guess what I was asking is that kind of net.
Yes. Yeah. I mean, another way of viewing what both monads and effect handlers are about is redefining the meaning of semicolon in a sense of sequential composition. The difference being with monads in Haskell, you do that by literally redefining the meaning of semicolon. With effects and handlers, you define the meaning at each operation. Anyway, yeah, if we run that, then it does the interleaving thing that we wanted. Okay, I'm wondering where I want to stop here. Oh, this is just to show you that you can easily augment the semantics with these parameters. I think I'm going to skip ahead to just leave you with these couple of slides. There's various researchy and less researchy programming languages that have effect handlers in, and some resources that are quite useful for learning more about handlers. This Jeremy's effects bibliography has links to everything. These two tutorials are very nice, and they're, I would say, still quite elementary, but much more mathematical than the presentation I've given here. And Daniel's thesis has quite a lot of sort of practical stuff on effects and handlers. Anyway, yes, I think I'll stop there and cover some of that. So, any quick questions?
The idea that you build up kind of syntax of the operation, don't give them handlers kind of, which means this feels like there's a lot of control. You can do all kinds of things. Is that a good thing? So, how do the method?
So, one way of answering that is to contrast it with, say, with delimited continuations, which allow you to do or conventional presentations of delimited continuations, which allow you to do very similar kinds of things. And one criticism there is you can do all this really powerful stuff, and you grab hold of the continuation, you could use it arbitrarily. What's nice about handlers is they force you to be very modular about it. You say the weird, fancy control stuff you're doing is very isolated in one place. So absolutely, you could do all kinds of weird and wonderful stuff, but you can see where it is. And actually, I think that does play out if you do more formal reasoning with these things as well. It's very modular. But yes, one perspective is this is just. I mean, what do you need if you want to implement concurrency? You need to be able to grab hold of continuations and switch them back and forth. So this is a structured way of doing that. Similarly, if you're wanting to do backtracking and so forth, you need to actually capture the continuation and run it more than once.